Yeah, hello again to the TRS-80 community. And it's still September 2024. That means we are still celebrating Septandy, all things Tandy Radio Shack, and in particular, of course, the wonderful line of TRS-80 microcomputer systems. Here we have my Model 1 on the bench, and it was released in 1977 by Tandy Radio Shack. That was their first ever personal home computer that consumers could acquire, and together with the Commodore PAD and the Apple II, these three systems that started the home computer revolution are nowadays also called the Trinity of the home computer revolution. So, and I'm happy to get update number 3 from my MIDI 80 MIDI sound and MIDI interface card in just on time before Septandy 2024 runs out, right? And yeah, so this is now the PCB revision 2. I needed to make a new board, and I no longer prototype these days with breadboards as I used to, because the PCB manufacturers in China, they are so fast, you know, within 1 week you actually can get a new version of your PCB back. So this is a previous version, right? And you see I needed quite a few of trace cuts and bodge wires. For example, I also figured I wanted one additional 5th LED, so I soldered that on by hand and so on. So yeah, in previous years I would have done all of this on breadboards, right? But I mean, given that this the turnaround time is really 1 week, and it only costs like $30 to produce a batch of 5. I no longer do breadboards, but I work like this, and I would say that the reliability of a circuit like this is still higher than that of a breadboard. So it's also certainly more fun to develop hardware like this. And yeah, so mostly no more breadboards for me. I mean, the sad part is that you are producing quite a bit more garbage, right? Because you always have to order 5 PCBs, and 4 of those usually end up in the trash until you have your final PCB revision. And so yeah, that's revision 2, and already there says 1 bodge wire here, right? So now I crashed the TRS-80 because I wiggled the port cable. So there will be 1 more revision, but then I'm basically done. And so that's good. And let me just bring the system back up again because I crashed it, but I don't want small LDOS, but I want LDOS. So let's boot LDOS again and then start basic again. And let me quickly remind you where we left last time. So I showed you that MIDI data output from the TRS-80 into the microcontroller, the Bluepill, into the S2 or the MIDI out DIN port is possible. And in particular, I showed you this simple drummer program in BASIC, right? And of course it's laggy because it's BASIC, but so I demonstrated that using output port 8 and basic out commands, we can basically send MIDI node on and MIDI node off messages even from BASIC, and that this direction output from the TRS-80 into the microcontroller worked fine. So just a reminder, a MIDI node on messages is 3 bytes, so 144 is where the MIDI node on messages start. Then you add the channel number, here it's 9, that translates to MIDI channel 10, which is the percussion or drum channel, right? And then you send the pitch, which is a drum number, in this case, and the volume. Then the sound plays, and it plays until you send the corresponding MIDI node off message. For a drum sound, of course, this wouldn't make a difference because those are one-shot sounds. But if you had a sustained sound like an organ or so, then this MIDI node off message would turn off the corresponding matching MIDI node on message. So yeah, and this is where we left last time. And then So outputting data from the TRS-80 into the microcontroller worked, but then of course I also need to read data back. And why is that? Well, because it's not only a MIDI sound card, but it's a MIDI interface, right? And that means you want to connect your keyboard, your synthesizer, and route MIDI data over the MIDI DIN input here into the microcontroller, such that the TRS-80 can read it then. And for this, of course, you use INP, right? And then port number, right? So you want to be able to read from port 8 as well as from port 9. And this is where I had problems with the previous design, and which required me to make one more new PCB revision. So the issue was that I couldn't reliably read or support the Z80 IOREAD requests with the Bluepill microcontroller, at least not in the way that I was using it, and would have been quite a bit of effort in order to get the timing right. See, the way that works is the Bluepill microcontroller has a number of GPIO pins, but it has only so many that are 5-volt tolerant, right? So in particular, I only have 8 available, and in order to support IOREAD as well as IOREQ requests, you then have to basically on the fly change the direction of these 5-volt tolerant GPIO ports from input to output. And this you have to do in the middle of a Z80 IOREAD request operation, right? So the default setting for these ports would be input. Then you see a IOREAD request, right? Something like the INP coming from the INP basic statement. And then the address decoder figures out, yeah, this is for me. It gets the signal to the microcontroller. Then the interrupt service routine triggers. And then now you have to immediately switch the direction of the GPIO port on the microcontroller from input to output and present the data such that the Z80 can read it back. And this timing is extremely delicate, right? And it also can involve halting the Z80 CPU. And indeed, I'm using this, but I looked at this on the oscilloscope, and the timing is so tight, and also there's jitter, like so it doesn't seem to be very reliable, the timing of the Bluepill. So I wasn't able to support this purely in software, right? Because the original design basically only had the Bluepill and the address decoder, but everything else was done in software, including the idea that you would just on the fly switch the direction of the GPIO ports on the Bluepill from input to output. And interestingly, the very same design worked on the Amstrad CPC version of this card, right? Because this is basically a port of the ultimate MIDI card that I designed, I think 5 years ago for the Amstrad CPC. And I had recycled and ported hardware that way before from the Amstrad CPC. For example, my Talker 80 speech synthesizer board, right, is also basically a port of a speech synthesizer that I did for the Amstrad CPC previously, Lambda Speak. And there, I mean, I had no issues basically at all supporting the same hardware design. But it seems that the CPC is not as is more forgiving when it comes to Z80 IOREAD and write requests. I guess it's pulling a lot of wait states the way the hardware is set up because of the video memory, whereas the TRS-80 seems to be running a protocol which is more timing critical, and I just crashed the machine, trying to switch from input to output and back to input during the Z80 IOREQ READ transaction, and I couldn't get it to work. And then I decided, okay, the solution here really is to add some extra hardware, and I did this in order to decouple basically the Z80 databus from the Bluepill databus. So I'm still switching direction from input to output because I have no choice. I don't have enough GPIOs. Otherwise I would need 16, right, if I had dedicated input and output ports. But I have decoupled now this single input-output Bluepill databus from the Z80 databus, because these chips here allow tri-stating, right? So they can the Z80 can just access the data when it wants it, and the timing is no longer that critical. So there's one latch, basically a flip-flop, right, a 47LS374, which latches the IO write requests that are coming from the Z80, and then there is a 47LS244, which is just an octal buffer bus driver, which is used to support the IO read requests from the Z80. And those are just being tri-stated and output enable selected when the Z80 wants it. So the Bluepill no longer has to be switching the port basically from input to output and back to input in such a way that the Z80 sees it. So the Z80 actually no longer sees the switch of the port direction on the Bluepill, and also given that it uses its own IO tri-stating select signals now on these chips, the timing is no longer critical and it just works like a charm now. So that means I can now show you a program that reads incoming MIDI data from the microcorg, right? Reads it, processes it in the TRS-80, and the TRS-80 simply echoes it back onto port 8. So let me load this program now. So this is basically a MIDI soft through implemented by the TRS-80. So let's see what's going on here. Very simple program. I have two ports. So the Bluepill, of course, has a buffer for incoming MIDI messages, right? Whenever you see such a blink here, that means a piece of MIDI data arrived and is being stored in the buffer. Of course, the buffer overflows at some point. It has a capacity of 256. And then with input 9, now the TRS-80 can check if there is a byte in the MIDI buffer available. If not, then it just keeps looping until a byte becomes available, right? And then the byte which is available can be read from port 8 using imp, right? Stored in the variable A. And then we immediately echo that back to port 8 output. So that way we are sending the data now from the TRS-80 into the Bluepill into the S2 or MIDI out. So yeah, let's run this. And the first thing it does is it clears its buffer. But now you see that the incoming MIDI bytes from the microcorg are being relayed and forwarded by the TRS-80 basic program. And of course this is laggy again, right, because it's just basic, but if this would run in assembly and machine code, then you would hear no delay. For example, there are no real chords, right? If I play 3 simultaneously here, then you hear that they are not being relayed simultaneously because there's a little delay. That's of course because BASIC is laggy, right? But this is not the firmware, right? In a previous video I demonstrated that this forwarding input to output rerouting of MIDI messages can also be done autonomously by the Bluepill firmware, right? But this is turned off here using one of the DIP switches. So the firmware is not doing this, right? You see nothing is happening. I actually need to run the TRS-80 program. So it clears its buffer now. But now so yeah, input and output for all supported ports 8 and 9 works now. And I actually don't know if 8 and 9 are good ports, right? I can easily change the address decoder, which is a simple GAL, right? Chip. So 16 V8 GAL. Or PAL, I think I should say, right? And so if you guys tell me, okay, oh, port 8 and 9 are not good ports because they are used by, you know, this and this hardware extension, then I can easily change that. But for now, I think the hardware is actually working the way it's supposed to. And I'm happy with that. And all what's left to be done is write assembly programs, right? I want to port the Z80 assembly programs that I have for the CPC, for the ultimate MIDI card, to the TRS-80. That is one general MIDI song player, so you can actually play complex general MIDI songs from the card. And also something like I have something like a simple MIDI recorder and playback program, right? So basically something like this, but not laggy and in assembly, and it stores the notes, MIDI messages in memory, and then it can play it back from memory. And of course you can also save them to disk, these songs, the recordings. So you basically have like a MIDI recorder and MIDI playback from memory. So yeah, and maybe I would even want to work on a MIDI sequencer, so that would also be a fun project. But for now, I think that's the update I wanted to share with you guys, and stay tuned. Thanks for watching, and yeah, it'll take a while to get the software up and running, maybe 4 weeks or so, you know, that's a hobby. But it's fun actually getting my feet wet with Z80 assembly programming. I mean, I did quite a bit of Z80 programming on other platforms such as the Amstrad CPC. But I mean, this is exciting. I'm really looking forward to get my feet wet with Z80, TRS-80 assembly programming. All right, until then, stay tuned, and thanks for watching, right? Bye.